In this lecture, we will actually analyze a graph. This graph represents the energy band in a crystal, as most semiconductors exist in the form of crystals. I hope you have already heard about what is Pauli's exclusion principle. It says that no two electrons in the same atom or electronic system can have identical values for all the four quantum numbers. First, we will understand the graph in general manner, then afterwards we will analyze it in a more technical way. Now consider this to be a silicon atom with the inner body representing the nucleus along with inner orbital electrons, which does not interact with other nearby atoms. The outer shell electrons are represented by blue spheres which interact with other atoms when brought closely to each other. These electrons are shown revolving around the nucleus. Now assume that few more atoms are also present such that central atom has shared all its four atoms such that its octet gets completed. Obviously, there is no way you can tell which electron belongs originally to which particular atom. But as per Pauli's exclusion principle, no two electrons can have the same identity. It is very obvious that crystals does not consist of only 5 atoms. Here you can see there are a huge group of atoms along with a lot of electrons revolving around them. Now, if you consider any electron in general, then there is no way that you can tell which electron belongs to which particular atom. Therefore, these group of atoms which together constitutes an electronic body working as a single system, there should be a way so that you can provide unique identifications for so many electrons. We also know semiconductors tend to lose electron easily after absorbing thermal or optical energy. For easier understanding, I have shown atoms to be spread linearly in a very regular manner. However, one s orbital and 3 p orbitals of silicon atom hybridized together to form sp3 hybridized orbital, resulting in tetrahedral shape. And if we talk about the crystal structure, then silicon, germanium and few other semiconductors are usually found in diamond structure. Free electron does not mean that they are roaming freely outside the crystal. It means that they experience very weak electrostatic force by nucleus of the atoms within the crystal, and when an external battery or potential difference is applied across the ends of a crystal, these are the electrons which move under the influence of electric field and contribute to conductivity. Now, we try to analyze the graph in a more technical way. We assume that we have n atoms in a crystal and we will ignore the inner level shells. In this graph, y-axis is representing the relative energy of electrons, whereas x-axis is representing relative spacing of atoms, or in other words, interatomic distance between the two adjacent atoms. Now, as you see in the rightmost part of the graph, where all atoms are acting individually, we have 2n electrons filling the 2n possible s orbital states all at the same energy level, and remaining 2n electrons are filling one third of the possible 6n p orbital states all at the same energy level. But this is true here only, as no two atoms are interacting with one another. And you know, practically it is not true for materials found in any state other than gas. Similarly, in crystals, atoms do interact with each other. So, this portion is not of interest for our study of energy band theory of crystals. But as the interatomic distance is decreased, the atoms will start exerting force on the neighboring atoms. Because of the coupling between the neighboring atoms, the atomic wave function overlap, and these atoms together constitutes an electronic system which must obey Pauli's exclusion principle. Hence, the 2n degenerate S states must spread out in energy. the separation between levels is small. But since n is very large, the total spread between the minimum and maximum energy may be several electron volts if the interatomic distance is decreased sufficiently. If we talk about n, it is of the order of 10 raised to the power 23 atoms per centimeter cube. This large number of discrete and closely spaced energy levels is called energy band. And as we move toward left, for enough proximity between the two nearby atoms, the 6n upper states merge with lower 2n states, giving a total of 8n levels, half of which are occupied by 4n available electrons. At this spacing, each atom has given up 4 electrons to the band. These electrons can no longer be said to be situated in p or s subshell of an isolated atom, but rather they belong to the crystal as a whole.